Hello students, welcome to EPG Pathshala. I am Professor P.N. Kodru from the University of Jammu. Today we are going to discuss about a module entitled as Bravais lattice and crystal structure under the paper Crystallography and Crystal Growth. The learning objectives are the symmetry elements exhibited by crystals are described here. The centrosymmetric crystals are illustrated. Symmetry about an axis is described. It is explained that crystals exhibit 2, 3, 4, and 6-fold axis of rotation. 5-fold symmetry is ruled out. Crystal form showing symmetry about a plane is explained. Combination of rotation and inversion through a point give rise to a different set of symmetry operation. Translational periodicity as the most fundamental feature of the Bravais lattice is explained. The concept of the fundamental building block is given. Symmetry elements and crystalline solids are described. Symmetry is the most general law inherent in the structure and properties of a crystalline substance. It is sometimes said to be properties of solid crystals. Most of the important properties of crystalline solids are structure-sensitive properties. There are certain laws of symmetry according to which the faces of a crystal are arranged, and this symmetry may be defined in relation to a center of symmetry, an axis of symmetry, a plane of symmetry. Let us take it one by one. Center of symmetry. A crystal is said to have a center of symmetry if, for a point within it, faces occur in parallel pairs of equal dimensions on opposite sides of the point and equidistant from it. Crystals exhibiting this symmetry are known as centrosymmetric crystals, example of which is shown in figure 2.1. Axis of symmetry, also known as rotation axes. If rotation of a crystal about an axis through 2 pi by n brings about the identical appearance of the crystal, the axis is said to be n-fold rotation axis. N can take values 1, 2, 3, 4, and 6. A rotation about an axis through 360 degrees will always result with identical appearance of a figure, and therefore the value of n is equal to 1 is meaningless. If n is equal to 2, the crystal has a 2-fold axis known as dyad. N is equal to 3, the crystal is said to have 3-fold axis known as triad. If n is 4, the crystal is said to have 4-fold axis known as tetrad. If n is 6, the crystal has 6-fold axis known as hexad. Figures that are examples of a dyad, triad, tetrad, and hexad axes are represented by the diagrams of figure 2.2. Figure 2.2 is a schematic representation of rotation axis. Examples of A, dyad, and B, triad. It shows figure 2.2, the schematic representation of rotation axes. The examples of C represent tetrad and D, hexad. Conventionally, The symmetry elements are represented by written symbols and graphical symbols for dyad, triad, tetrad, and hexad. The written and graphical symbols are 2 in the form of shown in the form of an ellipse, 3 shown as a triangle, 4th shown in the form of diamond, 6th shown in the hexagon, respectively. N is equal to 5 or 7 are not allowed in crystallography. Non-existence of symmetry axes other than 1, 2, 3, 4, and 6-fold in a lattice is actually based on the fundamental requirement for an arrangement of points to define a lattice, because the symmetry elements that are operational have to conform to their translational periodicities. A plane in the crystal which divides it in a way that the halves on opposite sides of the plane are mirror images of each other. One of the crystal forms exhibiting mirror planes is shown in a schematic diagram of figure 2.3. This symmetry element is represented by a written symbol letter M and graphical symbol within in the form of a dash. Figure 2.3 shows crystal form exhibiting mirror plane. Inversion axis. It involves a combination of rotation and inversion through a central point. The written and graphical symbols of inversion axis are 1 bar, 0, 2 bar, none. M is generally used because 2 bar is the same as a reflection in a plane to which two-fold axis is perpendicular, and therefore 2 bar is equal to M. 3 bar, 4 bar, 6 bar, respectively. 1 bar is actually identical to a center of symmetry described earlier, and therefore the symbol is used for center of symmetry. There are all the symmetry elements which may be exhibited by the external form of the crystal. Bravais lattice and crystal structure. A Bravais lattice is simply a lattice of points in space formed by repeating units. A Bravais lattice is just a discrete set of points in space which appears to be the same when one looks at it from any one of its points or when looked at from any other lattice point. A crystal structure is built up by placing bases down on each point of Bravais lattice. Basis actually is a single atom or ion or a group of atoms or a molecule. At each lattice point, one finds an identical arrangement and orientation of the bases. The crystal then develops by repeating the bases in space in accordance with the requirements of a particular Bravais or space lattice involved. Translation vectors. Translational symmetry or translational periodicity is the most fundamental feature of a Bravais lattice. Let us consider Bravais lattice of figure 2.4. There are 3 vectors A, B, and C which correspond to elementary translations along 3 different directions. The elementary translation vectors A, B, and C are as shown in figure 2.4. Here A vector represents shortest period in the lattice. B vector represents shortest period not parallel to A vector, whereas C vector represents the shortest period not coplanar to A vector and B vector. Translational symmetry or periodicity can be understood as follows. Consider R vector to be any position in the lattice. There would be location of some point on the position R vector which is derivable from R using the below given equation, that is R prime vector equal to R vector plus n1 A vector plus n2 B vector plus n3 C vector, represented as equation 2.1. The lattice arrangement has to be the same at R vector as at R vector as per the translational symmetry requirements. The translation operation is then obtained as T vector equal to n1 A vector plus n2 B vector plus n3 C vector, which is indicated here as equation 2.2. And then the same is added to the vector R. Equation 2.1 can be expressed in terms of an operator as T bar n1, n2, n3, R vector equal to R prime vector, which is indicated as equation 2.3. The totality of operations for all values of integers n1, n2, and n3 is called translation group for the crystal. The translation group is a part of the space group that includes both translation and rotation operations. The translational periodicity described above is in terms of the vectors A, B, and C, which define the edges of the primitive cell. The primitive cell of a Bravais lattice is a unit cell which contains at most one lattice point. We will discuss unit cell. A unit cell is a small unit of the crystal which, on repeating in space, forms the entire crystal pattern. It is the fundamental smallest unit of which the entire crystal is built up. Let us consider a lattice in two dimensions as shown in figure 2.5, which shows three primitive cells 1, 2, and 3. Cell marked 4 is a non-primitive one. Notice that 4 different cells marked 1, 2, and 3 are primitive, whereas cell marked 4 is non-primitive. The primitive cells are those which have atoms at their corners only. Though the primitive cells appear to have different shapes, they enclose the same area. Figure 2.2 represents the lattice of a two-dimensional crystal. The parallelogram, say marked 1, is determined by the basic vectors A vector and B vector. All translations of the parallelogram say 1 by integral multiples of the vectors A vector and B vector along the A vector and B vector directions will lead to translating it to a region of the crystal which would be just like the original one. This way, the whole crystal may be reproduced simply by translating the area marked 1 along A and B directions by all possible combinations of multiples of the basis vectors A vector and B vector. As such, every lattice point in the crystal could be described by a vector R vector, where R vector is equal to H A vector plus K B vector, H and K being integers. In the same way, one can extend the argument to define unit cells and basis vectors for three-dimensional crystal lattices. One is now in a position to define unit cell as a region of the crystal which is defined by three vectors A, B, and C, so that when the same is translated by any integral multiple of those vectors leads to a similar region of the crystal. A set of linearly independent vectors A, B, and C is used to define a unit cell. The unit cell enclosing smallest volume which is used to define a given lattice is called primitive unit cell, whereas the primitive basis vectors are a set of linearly independent vectors which defines a primitive unit cell. Every lattice point in a three-dimensional crystal lattice is described by a vector R defined as R vector equal to HA vector plus KB vector plus LC vector, where H, K, and L are integers. So, students, let us now summarize. The crystals exhibit symmetry about a point, a line, and a plane. The translational symmetry is the most characteristic feature of the Bravais lattice. Crystals showing symmetry about a point are known as centrosymmetric crystals. Crystals show symmetry about an axis. Congruency is achieved on rotation about an axis through an angle of 180 degrees, 120 degrees, 90 degrees, and 60 degrees, and are designated as dyad, triad, tetrad, and hexad, respectively. The possibility of achieving congruency by rotation about an axis through 72 degrees is ruled out. Crystals show plane of symmetry, also known as mirror planes. The concept of unit cell as the fundamental building block of the crystal is described and discussed. Thank you.